Welcome back to the video series on integration and differential equations. In this video we're going to do some mixed practice. The plan is that I'm going to recall 4 of the formulas that we've seen over the previous videos, and we're going to run through some examples and try to decide which formula applies in which case. So this will be helpful for getting you organized for writing a test, because typically on a test you won't be told which formula to apply for which problem. First formula we saw was how to integrate u to the n. So for short, let's just refer to that as the power or the power form. Next formula we saw was how to integrate du over u. We called that the ln form. More recently, we talked about the inverse trig forms. Notice here that I'm using a special case of this formula. We're using the case where a equals 1. So we've got the integral of du over the square root of 1 minus u squared, and that gives us arcsine of u plus c. Again, remember that a is 1, so we're looking at a special case of that formula. So let's call that the arcsine form. And related to that, we saw the arctan form, and I'm also presenting that form with the value a equal 1. So the reason why I choose a special case there is just because it gives us better practice in being able to identify which form is which. Essentially, the formulas are going to look more similar when we make the choice a equal 1, so it will result in better practice. So for each example that follows, we're going to identify the correct form. The options are power, ln, arcsine, arctan, or none. So here's our first example. So we've got the integral of dx over 1 plus x squared. So the correct answer here is arctan form. Let's see why that's the case. Formally, what you could do is you could substitute. You could let u equal x. And so if we ran through all the details here, we let u equal x, then we'd be able to rewrite this integral as du over 1 plus u squared, and then yes, it would look exactly like the arctan form. But it would be better to be able to do this a little bit more quickly. Essentially what you can say to yourself is, hey, this is just the arctan formula with a different variable. Instead of calling our variable u, we're calling our variable x. Other than that, it fits the arctan form exactly. So let's compare that to example B. What if I modify this a little bit and put a factor of x in the numerator? Okay, so the correct answer here is ln form. Let's see why that's the case. The substitution we would make here, let's maybe just draw a line to separate this a little bit. The substitution we would make here is to sub u equal the entire denominator. So u would equal 1 plus x squared. And if we went through all the details of that substitution, we would be able to rewrite this integral as 1/2 du over u. And so that fits the pattern of the ln form. More intuitively or more quickly, you should be able to recognize the ln form when you've got a function on the bottom and you've got its differential, or possibly a multiple of its differential on top. So we've got 1 plus x squared on the bottom. There's no power being applied to that. There's no square root. It's not being raised to a cube or a 4th power or anything like that. It's just the first power of this expression, 1 plus x squared in the denominator. And then its differential would be 2x dx. We're seeing a multiple of that on top. So that's the quick way to recognize the ln form. Part C, we've got the integral of dx over the square root of 1 minus x squared. So that is the arcsine form. If you wanted, you could make the substitution u equal x, just to rewrite it so that it exactly matches this formula, but in my opinion that would be overkill. It's best just to look at this and say, hey, this is exactly the arcsine formula. The only difference is that we're calling our variable x rather than calling it u. So I wouldn't recommend going through all the details of the substitution there. Okay, part D, let's see what happens if we take part C but we introduce a factor of x into the numerator. Now, what type of problem is it? Well, the correct answer is power form. To see the details of that, we would choose u equal the quantity that's being raised to the power. In this case, it's a square root that's acting like the power, so the substitution we would make is u equal 1 minus x squared. And if we were to rewrite our integral, without showing all the steps here, I'll just jump to what you would get. It would look like minus 1/2 du over root u. So yes, that certainly fits the power form. We've got a power of u multiplied by du inside our integral, and that makes it an instance of the power form. So quick way to recognize that. In taking a first glance at this integral here, we see that we've got a quantity raised to a power. Our quantity is 1 minus x squared, and then we're confirming that we've got either the differential of that quantity or at least a multiple of that differential. So if you're off by a factor of 2 or a factor of 3 or a factor of half, that's fine. That can be corrected in your substitution, but you should have a multiple of that differential on top. So yes, that fits the power form. And then finally, part E. Suppose we look at the integral of dx over the square root of 1 plus x squared. So the correct answer here is none. This fits none of these patterns. Let's run through them and understand why. So it's not the power form, because for the power form we would need x dx on top. So if you try to go through with a power type substitution, you will not be able to complete the substitution. So it's not power because we've not got that x dx on top. Okay, it's not ln form because in the ln form your variable should not be raised to any power. So not ln form. It's not arcsine, although it looks close. The problem is the sign in the square root. So for arcsine you need a negative sign in the square root, so it's not arcsine. It's not arctan either. For the arctan form you don't want a square root in the denominator. We've got a square root here. So it's not arctan form either. It is, unfortunately, none of them. So the best way to get comfortable with identifying the correct technique is, of course, just doing lots of practice. The more practice you do, the more quickly, the more easily these patterns will sink in and be recognizable to you when you see a new problem.